All right, we are going to be graphing both f of x equals ax squared and also f of x equals ax squared plus c. So let's take a look at this first example here. It says graph g of x equals 2x squared. So we want to start with a table of values so that we can create some ordered pairs that we could then plot in our coordinate plane. So we've got here x equals -2. Now if x is -2, then we've got -2 squared, which is 4, and we multiply that by 2, so 2 times -2 squared equals 8. Okay, then the next one, we've got -1, so -1 squared would just be 1, and 2 times 1 would be 2. Then we have 0. 0 squared is 0, and 0 times 2 is 0. Then for 1, 1 squared is 1, and 1 times 2 is 2. And then for 2, 2 squared is 4, and 2 times 4 is 8. So now we can plot these points in our coordinate plane. So we have -2, 8. -1, 2, 0, 0, 1, 2, and 2, 8. Then we just want to, as we're drawing this graph, do our best to draw a smooth curve through these points. It's not the easiest to do, but just approximating our graph here, so that's okay. Okay, now the vertex of this graph, right, we can see the very bottom, the minimum point of our graph is at 0, 0. So that's our vertex. Now the axis of symmetry, we can see, will be x equals 0. Our domain will be all real numbers. And our range, we can see nothing is ever going to be below 0 because that is our vertex. So our range will be y is greater than or equal to 0. Okay, and then we want to compare this graph to the graph of f of x equals x squared, our parent function. So if we were graphing x squared, we would again have a point at 0, 0. We'd have a point at 1, 1, and 2, 4. We could also see one that would be at 3, 9. So we can see that our red graph, g of x, is going to be a vertical stretch of our parent function, f of x. Okay, and that makes sense. If we're looking at this function 2x squared, right, we're taking x squared and we're multiplying it by 2. So each of those values is going to be larger. So for example, right, with our parent function, f of x equals x squared, you simply have 1 squared, which is 1. But then for this new function, g of x equals 2x squared, when x is 1, you're then also multiplying that by 2, so it becomes a larger number, and that would continue for the rest of this function. All right, now looking at this next one, we are going to graph f of x equals -1/3 x squared. You'll notice for this table of values, I've chosen x values that are multiples of 3. That'll just make our calculations easier in terms of squaring and then finding a negative 1/3 of these values that are multiples of 3 rather than multiples of 2 or another number. So we start with negative 6. So we've got negative 6 squared, which is going to be 36. And then negative 1/3 times 36 will give us negative 12. Okay, our next value, negative 3. So we have negative 3 squared, which is positive 9. And then negative 1/3 times 9 would be negative 3. Then we have 0. 0 squared is 0, and 0 times negative 1/3 is 0. Then 3 squared is 9, and negative 1/3 of 9 is negative 3. And 6 squared is 36. Negative 1/3 of 36 is negative 12. So now we can go ahead and graph this. So we've got negative 6, negative 12. So here's negative 6, negative 12. Then we have negative 3, negative 3. And 0. And then we have 3, 3. Sorry, 3, negative 3. And 6, negative 12. And so for this one, we can see that this is concave down rather than concave up like the parent function f of x equals x squared. And we can see that is because of this negative a value. So we're multiplying negative 1/3 times x squared, and that's causing this graph to be concave down. If we were to compare this to our original parent function again, that's f of x equals x squared, right? We can see it's a reflection in the x-axis and also a vertical shrink by a factor of 1/3. Moving on to our final graph that we will look at for today, we're going to graph f of x equals 4x squared plus 1. So now we're adding in this c value for our function in the form ax squared plus c. So again, we'll start with our table of values. So we have negative 2. So if we substitute that into our function, negative 2 squared would be 4. 4 times 4 is 16, and 16 plus 1 is 17. Next, we have negative 1. So negative 1 squared would be 1. 1 times 4 is 4, and 4 plus 1 is 5. Then we have 0 squared is 0, times 4 is 0, plus 1 is 1. Then with x equals 1, we will again get 5, and with x is 2, we get 17. So we can go ahead and graph that. So at negative 2, we have 17. At negative 1, we have 5. At 0, we have 1. And then 1, 5, and 2, 17. We can graph it. And you'll notice, right, this plus 1 here, as you saw in your exploration, this plus 1 has caused the entire graph to shift up by 1 point. Now again, I want you to see why this function, why this plus 1 is causing that. And again, it makes sense because we're taking this whole formula, right? We've got our x squared, and we multiply that by 4 in this case. And then whatever value we get, we add 1 to it. So it's going to shift every value that we would normally have with our parent function and shift that upward. And we can see that if this were a negative number here, if we were subtracting, for example, if we subtracted 2, we would see that everything would shift down by 2 instead. So if we were to compare this again to our parent function, right, that would be at 0, 0, 1, 1, negative 2, 4, negative 3, 9, and 3, 9, and negative 4, 16, and 4, 16, and we can go ahead and graph that as well. So we can see 4x squared plus 1 is a vertical stretch by a factor of 4. And we can also see it is translated 1 unit up from our parent function f of x equals x squared. You can see that they still both have the same axis of symmetry, which is x equals 0. You can see that they have the same domain, which would be all real numbers. However, their range is slightly different because the range of our parent function, x squared, would be y is greater than or equal to 0. And for this one, since our vertex is at 0, 1, this would be the range would be y is greater than or equal to 1.